Hello to everyone. Welcome to the lecture of fourth lecture, in which this lecture I will discuss about charge carriers in semiconductors. Charge carriers, the charge carriers can be of two types, that is electron and hole. In my previous lecture, I have told you about the EK diagram. Okay, I have told you about the EK diagram in which we have plotted the energy of electron with respect to its position k. I have plotted EK diagram in previous lecture. So what is EK diagram now? If EK diagram is not if EK diagram I have said that the position of Fermi level is totally statistical. Position of Fermi level is totally statistical. So number of electron at a particular energy state can be given by at that particular state the occurrence of probability of that electron. This is a Fermi level which I have discussed in next class, and today I will discuss it also and solve some numerical also on that. So Fermi level, value of Fermi level from point, and the distribution of electron. Similarly, if I will talk it about the hole at particular energy level, then what should be the GNE into 1 minus F of E, means whatever the probability of occurrence of electron is there at the same moment, the probability of occurrence of electron with 1 minus sign, then it will be a probability of occurrence of hole. This will be a probability of occurrence of hole, and here you can see that it is showing the probability of occurrence of electron. So in that way we can say it. So if I want a number of electron present at a particular state, then what should I know? I should know the Fermi level, the value, the Fermi distribution of electrons or holes with Fermi level. Okay, distribution of electrons and holes with the Fermi level, and this multiplication will give the exact value of electron or hole at a particular location. So this must be required. So as I have drawn one diagram as this one, conduction band, valence band, conduction band, and Fermi level, intrinsic, like that I have drawn. And after that, if I have merged it with a Fermi delta function, then how I can do it? With that then 0, 1 by 2 and 1. So as I have said that at the Fermi level the probability of occurrence of electron is 1 by 2. So, okay, so now the Fermi delta function is like this only. Okay, this is there like that. So if the Fermi level is coinciding with EI, then it should be like this one. Okay, so depending upon that the position of the location of that one is decided. Okay, now let's if I will go for the mathematical calculation which are required for the calculation if I will know about the number of, generally I am interested about the number of electrons or holes which are active during the time of conduction. I am not interested about the electron and hole which will remain idle and not be playing participation into the conduction. So N0 will be, if I am talking about electron, the N0 will be its distribution function multiplied by its Fermi level with dE. Okay, now F of E, as per you know, that it should be equal to 1 upon 1 plus exponential E minus EF upon KT. E minus EF upon KT, which can be further simplified to as exponential minus of E minus EF upon KT. Okay, so now if I will know the distribution function GCE, then I can multiply it by this quantity. So I can get the value of n naught at a particular energy level. Okay, so how we can do for that? N naught should be equal to EC to infinity 4 pi 2 twice of mn asterisk upon h cube under root E minus EC exponential. I am talking about the point at the conduction band. So now I have taken that point E minus EF upon KT with up to which level I will integrate? I will integrate with respect to D. So okay, so 4 pi to mn asterisk under root E minus EC upon h cube into exponential E minus EF upon KT. Okay, so if I will what is mn asterisk? Mn asterisk is mass of electron, an effective mass of electron. Asterisk denotes the effective mass of electron. So if I will solve this equation, then I will get n naught will be equal to 2 pi mn asterisk into KT upon h square into exponential with minus sign EC minus EF upon KT. I have integrated ED with respect to EC. Then after integration I have got this quantity. So this quantity may relate to NC. So now NC will be equal to N naught will be equal to N naught will be equal to NC into exponential E minus EF upon KT. Okay, with a minus sign EC minus EF upon KT, and this is 3 by 2 h cube. Okay, this quantity within cube by 2. Okay, so n naught is in like this way, and n naught is equal to NC exponential minus EC minus EF upon KT. So value of n naught will depend upon NC. One more thing I want to tell you, that whether it is depending upon any way, but one thing I want to tell you that that it is also depending upon the temperature. Now the value of NC should be how much? 2 multiplied by 2 pi mn asterisk into KT upon h square to the power 3 by 2. Okay, now see here, if I have kept this quantity as like this one only, now mn asterisk is and all the quantities are within under root, and within t to the power. So now NC is dependent upon t to the power 3 by 2. Okay, NC is dependent upon 3 to the power 3 by 2. And not in n naught, I have written the value of n naught as NC exponential EC minus EF upon KT with minus sign. Okay, I have written this value. So here it is also exponential term is also depending upon the temperature, and NC is also depending upon the temperature. And how much quantity it will depend? It will depend to the power of 3 by 2. NC is dependent upon temperature at the power of 3 by 2. So the number of electron in conduction band generally depends upon the temperature to the power 3 by 2. Now suppose if I want to calculate, calculate the now go through one question. I am going from one question from Nieman book. Okay, calculate the probability that a state in the conduction band is occupied by an electron and calculate the thermal equilibrium electron in silicon at T is equals to 300 Kelvin. Okay, 300 Kelvin means we are going for room temperature. Okay, so at room, whatever the quantity, we will generally know at 300 Kelvin, so it will not be an issue for us that how we can do. So for that, if I have to do this equation, then how firstly I have to perform. First of all, I require the Fermi level. Okay, so it is given as 0.25 difference with the conduction band. So Fermi level at EC should be equal to 1 upon 1 plus exponential. Okay, and what the quantity here is given. Assume the Fermi energy is 25 electron volt below the conduction band. So now what the reference they have given? The reference they have given is the conduction band. So what should I do? EC minus EF upon KT. Okay, which I have further simplified it as, I can simplify it as exponential minus of EC minus EF upon KT. So now the difference EC minus EF is as given as how much quantity? That is 0.25. Okay, the exponential will be minus 0.25 divided by 0.0259 electron volt. Okay, so now the quantity, this quantity has came as 6.43 into 10 to the power minus 5. So now you can see here that the probability of occurrence of electron at this particular energy level is very low. It's very low. And now if I will multiply with this N0, what is the value of N0? NC generally value of NC is 2.8 into 10 to the power 19. Okay, then I will multiply it by this quantity, then I will get the answer as multiplied it by this quantity, 6.43 into 10 to the power minus 5 multiplied by 6.43 into 10 to the power minus 5. Then I will get how much? Then it is showing the result 1.8 into 10 to the power 15 per centimeter cubic. Okay, so you can see here that even the probability of occurrence of electron is very low. Even though I have got so large number of carriers here. Why it is like that? Because of a higher number of carriers are present in the conduction band. Okay, so that's the reason that we can know that one, how we have to do for that. If the number of electron is higher, number of electrons are higher, like 2.10 per 19, so a small fraction of probability can occur large number of electrons. So this is a simple equation which was never deviated from the temperature. Okay, suppose one question I have given, and it is asking about the temperature, different temperature at 400 degree Kelvin. So how we have to proceed for that question? Like I have told you that which thing is going to be differ. Like in the case of NC, you can see here like 2 into 2 pi m(n)* into KT upon h square. H square is all, it is Planck constant, 2 pi m(n)* cube, but it will not going to be changed for a different temperature. It should be same. Now in KT the temperature has to be different. So what I can do, like for different temperatures, suppose at NC1, what is NC1? NC1 is the temperature that is 2.8 into the power 19 at 300 Kelvin. Okay, at 300 Kelvin temperature. So 2.8 10 power 19 is at 300 Kelvin. So how it relates with the NC1 quantity? So NC1 is equals to T1 to the proportional to T1 to the power 3 by 2. If I will omit the proportionality, I will go for some constant. Now NC2, which is at 400 degree Kelvin. Okay, so now kk will be cancelled out, so kk will be cancelled out, and now T2 to the power 3 by 2. In this case, which thing is unknown for you? NC1 you better know, that is 2.8 to the power 19, and T1 you will know, T1 is at 300 Kelvin. T2 you know, NC2 you didn't know. Okay, NC2 you didn't know. So you, by having 4 variables, 3 are known, so you can easily get the value of NC2. Okay, so you will easily get the value of NC2, and now things will be clear for you. How you have to proceed. Now one more thing, like this is KT. Okay, this is KT, and I have to put this value in electron volt. Okay, in electron volt. Suppose you didn't remember the value of KT, then how will you proceed for that? I have told you a quantity KT by Q. If you have remembered in last lecture, 26 millivolts something I have told you, lowest quantity on which I have normalized the thing. Like see here, EC minus EF, difference between conduction and valence, is again going to be normalized with respect to KT. So now KT by Q, KT1 by Q is equals to, what is the value of KT1? You know, that is 26 into 10 to the power minus 3. It is at which temperature? It is at which temperature? It is at 300 Kelvin. Okay, so now if I will talking about another temperature, then it is KT2 by Q. Okay, so now it is X for me. So K will be cancelled out, Q will T1 upon T2 will be 26 divided by X. The X can be easily calculated. So here I have shown you that suppose you have a different, suppose you have different at different temperature, the calculation can be done more easier. But one thing is required, that you have to keep it in mind, that which thing is dependent, if I am talking about conduction band, how it is going to be dependent on the temperature and at which power, then you can easily do that. Otherwise you have to solve for whole. Okay, so I think this thing will help you. One thing more, that NC, the value of NC similarly I have done for NC. Similarly I can also do that for conduction valence band. So the value of NV for that is NV for that 1.04 into 10 to the power 19. The value of NV is 1.04 to the power 19, and value of NC is 210 to the power 19. So you will have to remember at least these values. Okay, now let I will discuss the value of NC, NV with respect to different material. As I have told you, SI is generally preferable, but in under which circumstances, so you should know. So that for that NC, the value of NC, as I have told you in previous numerical, is 2.8 to the power 19. The value of NV is 1.04 into 10 to the power 19. The effective mass of electron with respect to normal one, that is 1.08, and here you can see it as 0.56. Okay, MPS by mn0. Similarly, if I will say about GA as gallium arsenide, then that I have to 4.7 into 10 to the power 4.7 to the power 17, 4.7 to the power 17, and 7.0 into 10 to the power 18, and 0.067 and 0.48. Amnestic upon M0 is 0. Now if I'll talk it about germanium, then in germanium I had NC is equal to 1.7 0.19 6.0 into 10 to the power 18, and it is now 0.55 and 0.37. Now see here what you have seen, that the band gap of Si is 1.1, the band gap of germanium is 0.6 or 0.6 or 0.7, like for the germanium, and for GAS one is this 1.42. For GAS it is 1.42 electron volt. So you can see here as the number of as the number of electron is a little bit more than GAS, is the reason that the band gap is more in GAS as compared to SI. So how much I have got? 2.10.119. Similarly for NCNV, in germanium it has it has its own property, so that's why it is like this only. So as I can see here, that the number of electron and the number of carriers NC and NV are also good, and the division of M and S3 was electron effective mass with to its normal one. And if I will talking about that electron effective mass with respect to its normal one, then how much I have got? Then I have got that is value is 1.08, or while the value of MPS3 is 0.56, while it is much lighter. You can see it is much lighter, loosely bonded, 0.067 and 0.48. But the main problem is that it didn't have the conduction band or valence band maximum electrons or maximum holes are available. So generally these may be the values. So why we will use conduction band, or why we use SI. If I will multiply both the equation which I have written, and then I will got Ni square equals to NCNV exponential minus of EC minus EV upon KT. Okay. And the difference between NCNV minus NV is called as NCNV exponential, and the difference between these two is called as that is EG. That is called as what we can say it as EG upon KT. EG upon KT, band gap divided by KT. So this is the band, and Ni. Now Ni is directly proportional to under root of minus exponential minus EG upon KT. So if the EG value is more, inversely proportional to that. So if Ni of SI is moderate as compared to GE, germanium has more value of intrinsic carrier concentration as compared to SI, while the GAS has lesser number of intrinsic carrier concentration than SI. So it will depend upon the band gap. So band gap is a major factor for deciding this situation. Now the value of SI for SI in value of SI for intrinsic concentration is 1.5 into the power 10 per centimeter cubic. Okay, for GAS gallium arsenide it is Ni is equals to 1.8 into 10 to the power 6 per centimeter cubic, and for germanium I have got Ni will be equal to 2.4 into 10 to the power 13 per centimeter cubic. Okay, so now you can see here for SI I have the highest one number of free carriers are available, highest, or we can say moderate is available, while in the case of GAS I have guessed lowest and germanium highest. So it will cause also large leakage current and all those things. So that's why generally we will go for SI type semiconductor. Now in this lecture I have discussed about the valence band, distribution of electron and holes in valence band and conduction band with respect to their probability function, f of probability, And now I have shown you this thing, like a value of intrinsic carrier concentration. Now in my next lecture I will show you generally what happened, like when we will draw conduction band and valence band, then in intrinsic carrier concentration we will draw EI in mid, but it is not in mid, it is slightly shifted from its original position, maybe in millivolt, but it is shifted, not in the exact center. It is the main reason. So how much it is shifted and how we can decide that it is shifted from its position, I will show you later on about this one. Okay, I will show you later on about this one in my next lecture. In this lecture, the main thing is that firstly you have to be familiar with the NC and the value of Ni. You should remember three values at least for SI, NC, NV, and Ni for solving the numericals and all. Numerical I have shown you that the value of Ni is 1.5 10 to the power 10. Similarly, if you will use for epsilon is equals to what? How much? Epsilon r into epsilon naught. If epsilon r is required, that is relative permittivity. For SI it is 11.8. You must remember this value. And what about epsilon naught? Epsilon naught is 8.854 into 10 to the power minus 12. You have remembered in MKS. But now you have to work on minus 14. Why it is like that one? Actually what happened, like 10 to the power minus 14, value of 10 to the power minus 14 is there. Why it is like that? Because I am doing in centimeter CGS, and it is better if I am putting the constant, and generally the values for solving the equation are given in centimeter only. So so for solving some numerical, it is required that you have to convert each and every value in meter, or you can put the constant in CGS. It will be beneficial for you, and it will be also less time consuming. So better to use 8.854 as epsilon naught into 10 to minus 14. Sometimes also happen that I have seen in the copies of the student, they will miss the value of epsilon or sometimes they will use this value only. But you have to remember that the relative permittivity is epsilon r into epsilon naught, which epsilon r is 11.2 in this one. Generally epsilon is used in the calculation, like for calculation of deflection width. These things are not this thing will be discussed in future also. A lot after 2 to 3 lectures when I will start diode. I think in next lecture I will show you that the intrinsic position is not in center, and then I will show you something about the bulk semiconductor, and then we will go for the diode. In this I will show you these equations and all. So for this class it is mandatory to go through the numerical with Fermi level, otherwise it will create always a confusion when we should put the value of f of e, when I will use how if temperature is changed, then how I have to proceed. If temperature is less, then how I have to proceed. So you please remember in that at room temperature the value is given like that. If I have to change a different value, then how I have to proceed. It is not like that you can do anything like for that. It is generally required that you have to see that the quantity how it is relating with the temperature. Okay, and I have also shown you the way from that you can calculate the value of at particular temperature without even knowing the value of constant. So these things can be applicable only when you people will know about the value of NC, NV. Okay, when you will people remember about the value of NC, NV, NI at least for SI at 300 Kelvin, then you can easily convert it into according to your temperature. So I think this lecture is beneficial for you, and now we will go for next lecture, and in this lecture I will show you the intrinsic Fermi level position. Intrinsic level position is not in center, it is a little bit shifted from its original position. So thank you for that. Thank you for this.